Hello, everyone. Happy Thursday evening or Friday morning, depending on from where you are tuning in, and welcome to the µTAS 2021 YouTube Live Research Teasers. We have been featuring worldwide recent developments in the microfluidic community from Europe and Africa in the morning, the Americas later during the day, and this session specifically focused on research from Asia and Oceania. I'm Anja Kunze, faculty at Montana State University, and I'm very excited to introduce our guests. We have Professor Wei Hou from Nanyang Technological University, Singapore, Professor Yi-Chin To from Queensland University Technology in Brisbane, Australia, and Professor Aram Chung from Korea University Biomedical Engineering. Welcome, everyone, and let's take it away with Dr. Hou.
So thank you, Anja. So hello, everyone. My name is Wei, and I'm from Nanyang Technological University in Singapore. So today I'll be giving a quick overview of our recent work, as well as to highlight some of the topics which we plan to submit for µTAS this year. So our group for the past few years has been working on developing integrated microfluidic platforms for single-cell impedance cytometry. As you can see on this slide, we have actually combined inertial cell sorting, cell focusing, as well as impedance detector on the same device itself. And this allows us to perform very rapid, like 5-minute electrical-based immune health profiling. We are currently validating this platform in different diseases such as diabetes. And this is also an example of a whole blood sample in, whole blood in, answer out platform, which do not require any sample preparation and is completely label-free. In another recent work, we have also reported that by controlling the sample inlet flow, we can hydrodynamically confine our target cells to the bottom half of the channel. This is especially good for impedance detector because our electrodes are located at the bottom. And so this allows us to measure the cells with greater sensitivity. And we have applied this for T-cell activation studies. So in a separate work, we further explore the capabilities of impedance cytometry for larger objects such as spheroids and microcarriers, and these are typically a few hundred microns in size. The motivation for this is in the space of biomanufacturing, whereby microcarriers are often used to scale up cell cultures in bioreactors. Typically in these bioprocesses, bulk sensors such as your gas sensors or your pH sensors will be used to monitor the cell growth. And if you have to look at the cells, you have to dissociate the cells from the microcarriers to do some optical imaging for cell viability or to perform flow cytometry analysis. And in this work, we report that we can actually apply the concept of impedance cytometer to look at the status of the cells and biomass in a label-free manner. So this is a chip we have developed for this work. It's a simple design, a one inlet, one outlet microchannel patterned with a coplanar electrodes using fused metal. As you can see on the slide, we have tried different biosamples such as cancer spheroids, hydrogel microcarriers, which have cells embedded inside the gel, as well as using commercial microcarriers such as cytodex to look at cells which are adhered on the surface. The advantage of our platform is as follows: is firstly, it is high throughput. We can run up to 1 particle per second. It's completely label-free, and we can detect the impedance signal at single particle resolution. And lastly, because this is operated in a continuous flow mode, this means that we can actually combine or integrate this with bioreactors in a closed loop and in a closed setting to perform real-time, remote, and even long-term cell culture monitoring. So for the upcoming µTAS, our group will be submitting a few abstracts related to the space in the field of biomanufacturing. On the left-hand side, we'll be submitting a few works exploring the capability and applications of this platform in looking at, for example, cancer spheroid drug testing, as well as looking at microcarrier proliferation and also stem cell differentiation on the microcarriers itself. We're also very excited to share another piece of work, which is on real-time actuated impedance sorter. And in this abstract, we're going to showcase our newer device and some of the results, as well as to highlight the obstacles we have faced and how we overcome them in issues related to real-time signal processing, as well as feedback control to actuate our actuators. So at this point, I would like to encourage everyone watching this video to submit an abstract for µTAS, as well as to ask your friends and colleagues to attend the meeting as well. As we all know, this year µTAS is operated in a hybrid mode, which means that, and it really doesn't matter whether we're going to attend the meeting in person or remotely, because the program has been catered to for both group of audiences to maximize the fun as well as to enjoy the conference. And this is also a good opportunity for us to support and be part of the µTAS community. It's always a good chance to catch up with old friends as well as to meet new friends from around the world. And of course, we are not forgetting about all the exciting talks by the leading researchers in this field who is going to share their breakthrough at this meeting. And last but not least, we can always wait until the pandemic is over for future conferences to have a beer together. But because science is brewing now, as we all are working very hard at the moment, so we definitely want to showcase our work and to interact with researchers so as to advance the microfluidics field in general. So with that, I have come to the end of my talk. So once again, I hope everyone will submit an abstract to attend the conference this year, and see you guys at Palm Spring or online. Thank you very much.
Thank you very much, Dr. Hou. This was a really great short research talk over here. And yes, I fully agree. We should be continue brewing science, and I'm very much looking forward to chatting with your colleagues and you in future. Thank you. And now the next one is going to be Professor Yi-Ching To.
All right, thank you, Anya. Hello, I'm Yi-Ching To from the Queensland University of Technology in Australia. So over the past few years, my group has been focusing on trying to develop microphysiological system for modeling multi-organ interactions. And during last year keynote lecture, I've presented on different device compartmentalization strategies on how we can grow different types of cells together and look at their interactions in the context of different applications. I've presented on a compartmentalized micro well array where you can have the reactive metabolites that's being generated by the liver interacting and targeting different cell types that are involved in skin sensitization. Separately, I've also developed we've also looked at development of a modular microfluidic perfusion system, and we can use such an approach to look at interactions between engineered microbial strain that produces butyrates and look at how it can reverse lipid accumulation in a fatty liver module. So for this year at µTAS, we are very excited to be presenting new results that is related on extending this modular perfusion system and look into mimicking metabolic crosstalk. And this work will be presented by my PhD student, Chung. So he will be showing you the construction of a muscle module, where essentially we have a device that contains a microwell arrays of 3D myobundles. And these muscle bundles are all sensitive to insulin. And separately, he is able to construct an adipose module. And these adipose module can be induced with free fatty acid to become a disease phenotype. And this can be indicated by increased inflammation as well as lipid accumulation. So you have to stay tuned to find out what happens when we connect this disease adipose module to the healthy muscle module. Besides compartmentalizing cells and their respective media in the system, we also set to ask whether we can have local oxygen concentration control, because different parts of our body are being maintained at different oxygen levels. So this work has been championed by my postdoc, Lewis, and he has taken a materials-based approach to try to formulate functionalized bioinks that are catered for anoxic, which is low oxygen, as well as normoxic oxygen conditions. And we're able to use microfluidic architectures to try to pattern this gel within a device and actually demonstrate its applicability in creating a microfluidic joint model where we can have co-cultures of chondrocytes, which prefers a low oxygen environment, together with osteocytes, which prefers a high oxygen environment. So I'm really excited to be attending µTAS this year, even though I may have to do it virtually from the other side of the Pacific Ocean. But nonetheless, I'm looking forward to reconnect and catching up with old friends. And as usual at µTAS, enjoy the great science that's being presented by both all the attendees as well as our plenary speakers. And I'm really happy and kind of to find out that this year, the conference organizers have worked so hard to try to cater to have events that is catered to the Asia Pacific time zone. So I'm very happy that I will be able to attend the conference during my working hours. So with that, I hope to see you at µTAS 2021. Thank you.
Thank you so much, Dr. To. This was a wonderful talk. And yeah, we are really looking forward to welcoming everybody here, in particular also the people who cannot travel and then hopefully can join us online. And now we are turning to our last speaker, which is going to be Dr. Aram Chung.
Okay, hope you can hear me. At the same time, thank you very much for this beautiful opportunity to share some of the ongoing research in my lab. Once again, my name is Aram Chung from Korea University, and why don't we get started? So if I have to put in a single sentence that what my lab has been working on lately and extensively is as follows. Yes, we create microfluidic device and that can actually deliver external biomolecules such as DNAs and RNAs, plasmids, and proteins and so on for cellular engineering to basically alter the cell's intrinsic function. You may wonder why we are working on this, and great example can be SARS-CoV vaccines. For example, AstraZeneca vaccine is delivering the DNAs into cells using viruses, and Pfizer and Moderna vaccine is delivering mRNA using nanoparticles. We want to do the same, but without the use of viruses, without the use of nanoparticles. We want to just deliver these external biomolecules into cells purely by cell and fluidic interactions that is happening in a microfluidic device, especially for cellular engineering. That's what we are working on these days. These are some of the recent developments from our lab. So the very left one, we call this as a microfluidic intracellular delivery platform. So the one you see on the left-hand side is already 3 years ago. And then the work is based on, hopefully you can see the videos and cells are coming from left to right in case you don't see them. And then they collide with a channel wall that has a little sharp tip. And then this tip basically opens the cell membrane and biomolecules dispersed in the vicinity can be transported to the cell. The center one is actually we deform the cells using the spiral vortex and vortex breakdown on intrinsic inertial flow phenomena happening in a cross slot in a cross junction here. And yes, here we were able to deliver the external molecules into cells quite effectively. And the last one on the right-hand side is we actually stretch the cells using the recirculating flows that is developed near the stagnation point. We're able to stretch the cells, which means we were able to open the cell membrane and nuclear envelope as well that can deliver extra molecules into the cells. So lately we are working on, we basically are using these platforms for cancer immunotherapy. Recently we are testing primary human T cells, T lymphocytes, and then we got really exciting results. And in terms of T cell transfection, and then we compared these results with our conventional tools such as electroporation and then liposuction. And then we are planning to present this in a µTAS 2021. And then lastly, another platform that I like to share is a new platform called droplet squeezing. We leverage droplet microfluidics with cell mechanoporation. So here, for example, cells are coming from left to right, and that cell suspension is mixed with external biomolecules of your interest. If you want to deliver DNA, you just need to mix with them with a certain concentration. CRISPR-Cas9 is another example here. And due to the surface tension difference, yes, cell can be encapsulated And as they go through a series of these small bottlenecks, we were able to deform the cells, and then an extra molecule can be delivered into those cells. Because of the use of droplets, we actually can resolve the channel clogging issue. At the same time, we were able to get really high efficiency due to the, again here, intrinsic small internal flow that is developed in a droplet at the same time. So if I show a quick real-time video here, the cells are being encapsulated. This is just again a sneak peek, and then as they pass through the small bottlenecks, and then as you can see here, really high throughput processes are available and really high transfection efficiency over electroporation and liposuction is presented. And another video here. All right, so if you're interested in, of course, please attend µTAS. And for me, µTAS means a lot. My very first µTAS was a really long time back in 2007 in Paris. I'm not sure you can see, but it was me. I was fortunate to give them a podium talk by the time. And then as a grad student, I was there. As a postdoc, I was there. Now as a faculty, I'm there, and I'll be there at the same time. Because the other previous speakers encouraged to attend, and I'd like to do the same. And it was just a great, I'm not sure you can see, but Anya's right here at the same time. All right, that's all I have. And then hopefully we'll see you virtually or in person real soon. Thank you.
Thank you so much, Dr. Aram Chung. Yes, and that's true. In one of the pictures, I was right there as well. Okay, so now I want to thank all of our guests again for sharing their work with us today. This was a really interesting trip into their research activities. Now, please join us again this Monday, May 10th at 3:30 EDT PM time for our next YouTube live sessions on µTAS 2021 workshops, exhibits, and sponsorships. And until then, please have a great weekend, and we hope to see you soon virtually or in person in Palm Springs here at µTAS 2021 again. Thank you. Bye.